Alright, people, we're back. Now, it's been a while, and I've had some thoughts. I've got plans for a video coming up, and I want to start competitive programming. I want to start doing some competitive programming. I feel like this stage of my life, I think it's the perfect time to learn about it. And maybe you'll see me play some Mahjong later today. We will see. Dean, let's go. My fellow friend. I won't out you. It's been so long since you last streamed. WB, thank you. Thank you, man. We'll get on to some stuff. I think I'll focus on dynamic programming today. Right. So let's see. Zahive, you're always there, man. Hello, long time no see. Truly. I might have to start learning C++ now if I'm going through the competitive programmer's handbook. I'll probably also do the CSES problem set while I'm learning. But I also need Leetcode here. Leetcode, actually. Because we still got problems to finish off. Bro, did you get the return offer from Amazon? Well, I would neither confirm nor deny as of now. Leetcode is greater than Leetcode. I know. Dean, I know you like Leetcode more than Leetcode. But I'm already too far gone. And also I'm typing with a new setup. I'm streaming with a new setup, I should say. We got a new Mac and we got a hub. Hard to actually show you, but actually I do have a screenshot. Let me try and find it. I think I'll just open it up. Another page. Alright, check it out. This is the new setup. It's kind of, actually I can't zoom in, can I? But this little box here, this little box saves a lot of wires from being exposed. And we got the Mac connected to this one wire, which is connected to the back of this. And then it connects to these two displays from this one wire. Pretty sick. Pretty sick. Okay, that's it. Bro, are you really going down this route? I thought you were trying to get a job. You're right. But maybe I'm at the next stage now. Maybe competitive programming is just the next stage of my life. Okay. Messages are showing up now, which is good. So things are somewhat working as intended. Okay. Now, because I want to learn dynamic programming, I want to just focus myself on the section on dynamic programming here. Probably we'll see how much we can get done, to be honest. Just learning about this stuff. Okay. So I will look at this coin problem. Maybe to the end of... Yeah, probably just to the end of that coin problem section. But it's probably going to be fast to get through this. It's probably just less than 10-minute read, surely. What happened to the Amazon internship? Don't worry. Don't worry, Zahib. It's good. It's good is what I'll say. We did some good work. I can't really say much else, you know, at the current stage. But I'll let you know if things change. Okay, so I think what would be good now is to do a dynamic programming problem. I probably won't be able to solve this dynamic programming problem that we're going to look at, right? And if we can't, then we'll look at that yes handbook to help us. Coin change 2. So this is a book on coin problems. The coin change 2 might be... I might be going into this book at the right position because we're going to be doing a coin problem. Let me read this problem and then I might, if I can't figure it out straight away, just read through this solution. Bro, winter here is coming to an end. Yeah. I mean, summer here still feels like summer, so I feel alright. Given an integer array coins representing coins of different denominations, $1, $5, and an integer amount representing a target amount of money. Return the number of distinct combinations that total up to amount. If it is impossible to make up the amount, return 0. You can assume that you may have an unlimited number of each coin and that each value in coins is unique. The amount is equal to 4 and you have the 3 different denominations, 1, 2, and 3. The different ways you can make the amount 4. So 4, 4, 4, 4. If you do 1 or 2 or 2, 1 and 3. If you have the amount of 7, coins of 2 and 4, you cannot make 7. That's fair. Now what's the coin change 1 problem? So the coin change, you're given an array, coins representing coins of different denominations. And an integer amount representing a target amount of money. Return fewest number of coins that you need to make up the exact target amount. If it is impossible to make up the amount, return -1. You may assume that you have unlimited number of each coin. So the minimum is 10 plus 1 plus 1. The minimum is nothing. Is a valid way to make up 0. Wow. Okay. I don't even remember how I did coin change 1. I'll open it up real quick. Okay, solved using backtracking, but too inefficient. Now I'm looking for a solution and seeing where to go from there. To make a dynamic programming solution, Leetcode explains a greedy approach. It's not solvable, but it's not solvable method, because if you have 1, 3, 4, 5 with 7 as a target. Okay. Leetcode then goes on the backtracking approach. So we get the top down, after watching the solution, I'm gonna cheat a little, but I understand it. So the recursive solution. I don't think I'll look into these in that much detail either way anyway. Give it a sec. I won't look into that clearly, but just have this coin change problem in mind. Hello copy multi, long time no see. How's the hype? I think you're not that interested on the dev side. Well, you are very wait, I can't word things. I am misunderstood. I am still very much into the dev side of things. But in order to improve, we must do some obligatory competitive programming. That's what I will say. Okay, but coin change 2. How would you even think about this problem to begin with? For example, backtracking approach. 3, 2. Out of all the given options, pick the largest one. I kind of think, but this is the count. So when it comes to this book, it does say something about these types of problems. The dynamic programming technique combines the correctness of complete search and the efficiency of greedy algorithms. Dynamic programming can be applied if the problem can be divided into overlapping subproblems that can be solved independently. There are two uses of dynamic programming: finding an optimal solution. We want to find a solution that is as large as possible or as small as possible. And counting the number of solutions. We want to calculate the total number of possible solutions, which, to be honest, is count coins 2. Finding an optimal solution, that is count coins 1, basically. We will first see how dynamic programming can be used to find optimal solution, and then we will use the same idea for counting the solutions. Understanding dynamic programming is a milestone in every competitive programmer's career. While the basic idea is simple, the challenge is how to apply dynamic programming to different problems. This chapter introduces a set of classic problems that are a good starting point. Tushar Utain, can you give us a productivity tour of your Mac, like what softwares you use and all? I am new to Mac and I don't have any idea about this. Well, there's not really, I wouldn't say there's really that many. Actually, I lie, there is quite a lot. But if there's any tool that you need for Mac, if you're a dev, you definitely just need Homebrew, right? For package management. Actually, I won't go on this side tangent now. I'll focus on the actual problem here. But maybe I'll do a little bit more of a productivity tour later. Keep that in mind. If not tonight, maybe tomorrow. Okay. So, cool. So there are two ways to dynamic programming: finding an optimal solution and counting the number of solutions. To be honest then, this is something I kind of want to take my own notes on as well, about dynamic programming in general. But I'm trying to think if it's worth just doing a couple of things. Firstly, saving this document. So Kasahara, evening man. Thanks for joining. It's still light. Hopefully where you and I both live. Okay. Man, I'm gonna get back to Leetcode as well. Come on. We'll get into it. Come on, we'll get into it. Let's go. I also do need to myself. So we're gonna have to reference the handbook. Probably gonna open this on a separate page. That makes the most sense. That's interesting. I did not know that's how it worked. We do not need that, definitely. What's your word PM on the glove? Currently, it's 90 words per minute, roughly. And it's equivalent to if I typed on the key on the normal keyboard, on the normal staggered keyboard. So they're equal. Not helpful. I don't know if there's any easy way for me to do this. Wait, were you at the security club store? Yes, I was. Yes, I was. The weird layouts look fun, but I can't be fucked switching between laptop. Yeah, that's fair. My laptop's like tucked away right now. Now, I don't remember how I did references. What's a good example I can reference? Cryptography and security. PDFs. So if I were to reference PDFs, we're looking at specifying the PDF name and then hash the page number. So CP handbook .pdf hash page 65. I'll call it CP handbook. Now that's 55. Oh, I see. I see how it works. This would be a 75. The 75. Unfortunate. Okay. Brendan found your stream and I got the same keyboard. Good luck, dude. Hell yeah. It's the Glove 80 Rex. It's the Glove 80 Rex. You know for sure YouTube's doing that on purpose. Okay, coin problem. You first focus on a problem that we have seen in chapter 6, given a set of coin values and a target sum of money. Our task is to form the sum n using as few coins as possible. The funny thing is, I'm just coming in at the perfect time. Just like slotting in, right? This is just slotting into my work. I mean, to my progress on Leetcode, the question that I'm currently doing, this is exactly the problem that I want to solve. So this whole problem is coin change, just coin change 1. In chapter 6, we solved the problem using a greedy algorithm that always chooses the largest possible coin. The greedy algorithm works, for example, when the coins are in the euro coins, but in the general case, the greedy algorithm does not necessarily produce an optimal solution. So this was also what Leetcode expressed as well, right? That was the thing that Leetcode was expressing. Now it's time to solve the problem efficiently using dynamic programming so that the algorithm works for any coin set. Dynamic programming algorithm is based on a recursive function that goes through all possibilities, how to form the sum like a brute force algorithm. However, the dynamic programming algorithm is efficient because it uses memoization and calculates the answer to each subproblem only once. I'm just thinking, hello KFC, I'm good, how are you? Could I just continue? Hello Bruce Wayne. Recursive formulation. The idea of dynamic programming is to formulate the problem recursively so that the solution to the problem can be calculated from solutions to smaller subproblems. I kind of want to come back to this greedy algorithm aspect, right? Coin change problem. To be solved in greedy algorithm, but being non-optimal is kind of not what I was expecting. Greedy algorithms, coin problem, okay. Maybe I will just quickly look at this, right? So a greedy algorithm constructs a solution to the problem that always makes a choice that looks the best at the moment. A greedy algorithm never takes back its choices, but directly constructs the final solution. Yeah, right. So for this reason, greedy algorithms are usually very efficient. For sure. The difficulty is in designing greedy algorithms. The difficulty in designing greedy algorithms is to find a greedy strategy that always produces an optimal solution to the problem. The locally optimal choices in a greedy algorithm should also be globally optimal. It is often difficult to argue that a greedy algorithm works. So in the coin problem, as a first example, we consider a problem where we are given a set of coins and our task is to form a sum of money n using the coins. The values of the coins are given and each coin can be used as many times as we want with the minimum number of coins needed. So the minimum number of coins, for example, if the coins are in euros and n is 520, all we need at least 4 coins. The optimal solution is to select coins 200, 200, 120. Sure. But the greedy algorithm, a simple greedy algorithm to this problem always selects the largest possible coin until the required sum of money has been constructed. This algorithm works in the example case because we first select 2 200-cent coins, then one 100-cent coin, and finally one 20-cent coin. But does this algorithm always work? Turns out that if the coins are in the euros, the greedy algorithm always works. it always produces a solution with the fewest possible number of coins. The correctness of the algorithm can be shown as follows. First, each coin 1, 5, 10, 50, and 100 appears at most once in the optimal solution. Because if the solution could contain 2 such coins, we would replace them by 1 coin and obtain a better solution. For example, if the solution would contain coins 5 plus 5, we would replace them by coin 10. In the same way, coin 2 and 20 appear at most twice in the optimal solution, because we could replace coins 2 plus 2 plus 2 by coins 5 plus 1. And coins 20 plus 20 plus 20 by coins 50 plus 10. Moreover, an optimal solution cannot contain coins 2 plus 2 plus 1 or 20 plus 20 plus 10, because we would replace them by coins 5 and 50. Using these observations, we show for each coin x that it is not possible to optimally construct a sum x or any larger sum by only using coins that are smaller than x. Let me read that again. Using these observations, we can show for each coin x that it is not possible to optimally construct a sum x or any larger sum by only using coins that are smaller. What the fuck? I gotta read this again. Using these observations, we can show for each coin x that it is not possible to optimally construct sum x or any larger sum by only using coins that are smaller than x. I need to break this down better. Let's just skip it for now. For example, I get the general gist. For example, if x is 100, the largest optimal sum using the smaller coins is 99. Thus, the greedy algorithm that always selects the largest coin produces the optimal solution. This example shows that it can be difficult to argue that a greedy algorithm works, even if the algorithm itself is simple. In the general case, the coin set can contain any coins, and the greedy algorithm does not necessarily produce an optimal solution. Correct. You can prove that a greedy algorithm does not work by showing a counterexample where the algorithm gives a wrong answer. In this problem, we can easily find a counterexample. If the coins are 1, 3, and 4, then the target sum is 6. The greedy algorithm produces the solution for 4, 1, 1, while the optimal is 3 and 3. It is not known if the general coin problem can be solved using any greedy algorithm. However, as we will see in Chapter 7, in some cases the general problem can be efficiently solved using dynamic programming algorithm that always gives the correct answer. However, it is possible to check in problem time if the greedy algorithm presented in this chapter works for a given set of coins. Or change making problem. Polynomial time. Okay. Cool. Okay. There's some new people. Hello guys. Letter XO. Are you still in college? Yes I am. I basically have 1 more year at the moment. Oh boy, the boy is live, yes. How do you know that Firefox? Bro, do you know that Firefox changed their TOS? I've heard, but I haven't looked into it yet. I know there's a video by... what's his name? I forgot his name. Mental Outlaw. And it's in my watch list. Do you know who won the speed typing comp at the booth? It was somebody that got over 160 words per minute. 160 words per minute. I don't know exactly who that was, but yeah. I think there'd be an announcement soon about that. And hello, Rawachi. I got your name right, hopefully this time. It is long time no see. Let's turn on this light. It's getting dark around here. Why no Twitch today? That's a good question. I just haven't set that up because this is a new machine. But also, I should be able to use this laptop for Twitch as well now, because it should be more efficient. Or it should be, it could handle another stream on it. Definitely the last laptop that I had couldn't that well. Can you do us a near fetch? I don't think I can say what a near fetch is. Okay. Right, I see. So it's just a way to show stuff, right? Oh, that's sick. Oh, so this is what people use. I understand it now. So this is what people use that I've seen. That's very cool. Are you still at Amazon? Not now. We are done with our internship. What? This is like a picture from... this just feels like a picture from Blade Runner. I'm hearing Resonance by Home when I see this. Loki, I'm interested to download this and show you. Brew, you say? Alright, let's just do it. Can I brew search for NeoFetch just to double check? Brew install NeoFetch. Why not join full time? Technically, I will not elaborate, but we are in the talks. Yeah, so these are the specs, I guess. Oh, packages, brew packages. You can see how many packages you have. That is cool. 64 is fair enough. Oh yeah, I got I got 48 gigabytes of memory on this machine. Yeah, I got a nice machine this time. Jealous of your typing skills. Nah, don't be, man. You're making me blush. Have you done ML, by the way? I've done intro to ML, if we're talking about subjects. I've done intro to ML, which is a master's course, which is similar, I believe, to the third year ML bachelor's course. 23 hours uptime. Yeah, this machine ain't gonna sleep for a while. If it's working fine, you know what I mean? I'm doing the 3rd year version this time. Good luck with that. Hopefully you find it more interesting than I did. Not to say it's not interesting. You know, it could be for you, like. I still found it okay, but you gotta know a lot of like high level concepts. You gotta know a lot of high level concepts from what I remember. Okay. Regardless, very cool. I'll keep this tool in my pocket. Sudo shutdown. I actually do like sudo reboots. When I was at Amazon and the machine just like froze on me, I would do sudo reboots. And I didn't know that you could do sudo reboots on a Mac. I know, that's like, you would expect it anyway. Because it's a Unix machine, right? But I never did it up until that Amazon internship, I guess, on their laptop, Mac laptop. Okay, cool tool, back to work. The thought is that a greedy algorithm doesn't work because, yeah, I need to read this sentence again, right? So, using these observations, we can show for each coin X that it is not possible to optimally construct a sum X or any larger sum by only using coins that are smaller than X. So in this sentence, right? Using these observations, we can show that for each coin X, say in this example, we're saying the coin is 5, that it is not possible to optimally construct a sum X or any larger sum. So it cannot construct a sum of 5 or any larger sum by only using coins that are smaller than this 5. Right, so you can't optimally construct this. Because you would use 5 as the denomination. You would use the 5 denominator, I would say. Yeah, okay, that makes sense. So for example, if you have 100, the largest optimal sum using the smaller coins. You are right. It's 50, 20, 5, 2, and 2, which is 99. Thus the greedy algorithm that always selects the largest coin produces the optimal solution. Damn. 50 plus 20 plus 20 is 90 plus 5 plus 2 plus 2. So yeah, there's 1, 2, 5, 10, 20, 50, 100. Yeah. So in this scenario, that makes sense. So it's like, so the coin change problem, if you had, you know, euro denomination, then you can solve this problem greedily. But if this if in the general case we don't have these set denominations, then we would have to use dynamic programming, and greedy algorithms just would break in this scenario to find our solution. Okay. Yeah, I can understand. Oh. So why do I hear tuk-tuk noises when you speak? That's... I can tell you why, actually. Our kitchen has the gas heater gas stove. And right now the ticking noise is like when you do this push down and you turn it, there's a small electric bolt that tries to start the fire. And that keeps on ticking right now when the gas stove is on. So that's just like a random fart of our house at the moment. So I apologize for the noise. Okay, recursive formulation. The idea in dynamic programming is to formulate the problem recursively so that the solution to the problem can be calculated from solutions to smaller subproblems. In the coin problem, a natural recursive problem is as follows. What is the smallest number of coins required to form a sum x? What is the smallest number of coins required to form a sum x? Let's solve x. Let's solve x to note the minimum number of coins required for a sum x. So the value of the function depends on the values of the coins. For example, if the coins 1 through 4, the first value of the functions are as follows. So for 1 to 10, we have 0 and 1, 1 and 1. So for 2, we'd just pick 1 and 1. For 3, we would pick 3. For 4, we would pick 4. For 5, we would pick 4 and 1. For 6, we would pick 3 and 3. 7, 8, 9, and 10. Yeah, I can see 10. For example, solve 10-3 because at least 3 coins are needed to form the sum 10. The optimal being 3 plus 3 plus 4. The essential property of solve is that its values can be recursively calculated from its smaller values. The idea is to focus on the first coin that we choose for the sum. For example, in the above scenario, the first coin can be either 1, 3, or 4. If we first choose coin 1, the remaining task is to form the sum 9, using the minimum number of coins. Which is a subproblem of the original problem. Of course, the same applies to coins 3 and 4. Thus, we can use the following recursive formula to calculate the minimum number of coins. So to solve x, we'd use the min solve x minus 1 plus 1, solve x minus 3 plus 1, and solve x minus 4 plus 1. I see. And you take the min because it is the min that you want. Man, this is genius. This is genius. Geniusly explained as well. So this is why people like this handbook so much. I can only appreciate it after having done coin change 1 and having to rely on Leetcode for those solutions. But reading it through text and not looking through a video, I think helps me learn it better. I'm glad that I'm going through this in a written form. So the base case of the recursion is solve 0, which is equal to 0, because no coins are needed to form an empty sum. For example, solve 10 is 7 plus 1. Solve 4, 2. Solve 0 plus 3. Solve 0 is 0. And so the answer is 3. Now we're ready to give a general recursive function that calculates the minimum number of coins needed to form a sum. So to solve for x, 0, so when x is 0, we return 0. If x is less than 0, then you have an infinity. That's interesting. So first, if x is less than 0, then the value is infinity because it is impossible to form a negative sum of money. Right, because then you can take the min of any of this and then it would be, wow. Yeah, it would still be taking the min and not the max. Right. So smart, so very smart, very intentional. So the min of the coins, so the min of all the coins, you solve given the x minus the coin plus 1, x is greater than 0. Okay. Then if x is the value of 0 because no coins are needed to form an empty sum. Finally, if x is greater than 0, the variable c goes through all possibilities how to choose the first coin of the sum. Once a recursive function that solves the problem has been found, we can directly implement a solution in C++. Constant inf denotes infinity. Still, this function is not efficient because there may be an exponential number of ways to construct a sum. However, next we will see how to make the function efficient using a technique called memoization. Memoization. So this is some function, solves. The solve function takes an integer x. If x is 0, then you return infinity. If x is equal to 0, you return 0. Or make best infinity. Okay. Oh, you just make it start at infinity, I suppose. And then for coins, in the coins, you do this recursively. The best is equal to the minimum of the best currently, which is infinity, so it's definitely not the best. And solve plus 1. So clear, so concise, so clear and concise. I can appreciate this now. You know, this is something that I can actually appreciate now, given that I've done so many Leetcode problems. And then we return best. Sasi Praveen, got a link for it. You mean this this book? Just search up Competitive Programmers Handbook. Would be the first link. Okay. Now, it says this function is not efficient because there may be an exponential number of ways to construct the sum. Right. And this is where we use memoization. So the idea of dynamic programming is to use memoization to efficiently calculate the values of a recursive function. This means that the values of the function are stored in an array after calculating them. For each parameter, the value of the function is calculated recursively only once, and after this the value can be directly retrieved from the array. In this problem we use arrays. So where ready x indicates whether the value of solve has been calculated, okay. And if it is, value x contains this value. The constant n, so this is up to n, right, has been chosen so that all required values fit in those arrays. Okay, now the function can be efficiently implemented as follows. Oh my god, that is crazy simple. This is the best handbook, man. On God it is. On God it is. The function handles the base case x is less than 0 and x equals 0. Then the function checks for ready has already been stored, and if it is, the function directly returns it. Otherwise the function calculates the value of solve x recursively and stores it in value x. This function works efficiently because the answer for each parameter x is calculated recursively only once. After a value of solve x has been stored in value x, it can be efficiently retrieved whenever the function will be called again with the parameter x. Time complexity of the algorithm is O of nk, where n is the target sum and k is the number of coins. But why? So you can only go for each of the coins. Yeah, so worst case. Yeah. No, yeah, worst case this makes sense because when you construct a number n, when you make a sum to number n, maybe the only coin you have is 1. K is 1. And then you need to, if n is, sorry, k will only include 1 in its set, n being the target sum, right? Wait, k is the number of coins. Yeah, n is the target sum. So then, if you only have k is equal to the set of 1 and n, you know it would be... How do I explain this? How do I explain this? Yeah, I don't think I understand how to explain this well. But okay, say k is only 1 and n is 50. Then you would have to go 50 times into the recursive function and then come back up. If n is 5, k is 2, k is 1 and 2, then you know you still need to search through k times. Right? Let me see this, actually. Note that we can only iteratively construct the array value using a loop that simply calculates all the values of solve for parameters 0 to n. So this is bottom up. Mart. Anyway, so value is 0. Value 0 is 0. For 1 to n, value of x is equal to inf and then auto c coins for every coin. If this is greater than 0, then the value is equal to the minimum of the current value or weight. So it's like the best value. So this is the best value so far. Calculate the best value, and if it's still the best value. In fact, most competitive programmers prefer this implementation because it's short and has lower constant factors. From now on, we also use iterative implementations in our examples. Still, it is often easier to think about dynamic programming solutions in terms of recursive functions. Okay, constructing a solution. Sometimes we are asked both to find the value of an optimal solution and to give an example of how such a solution can be constructed. In the coin problem, for example, we can declare another array that indicates for each sum of money the first coin in an optimal solution. Counting the number of solutions. Okay. This is good. So sometimes we are asked both to find the value of the optimal solution and to give an example of how such a solution can be constructed. In the coin change problem, for example, we can first declare another array that indicates for each sum of money, first coin in an optimal solution. And then we can modify the algorithm as follows. Is the given coin. After this, the following code can be used to print the coins that appear in an optimal solution for the sum n. Why? So while n is greater than 0, okay, right, so this is just how to print something in C++, I'm guessing. Yeah. That does make sense. This is a very cool way to do things as well, like, very cool. Like, what do you call this data structure? You know what I mean? An array. Really? I mean, yeah. Alright. And then count the number of solutions. So now let's consider another version of the coin problem where our task is to calculate the total number of ways to produce a sum x using the coins. For example, if coins 1 through 4 and x equals 5, there are a total of 6 ways. Yeah, actually, yeah, that checks out. Right, we're not talking about combinations, but how many different ways we can construct the given 5. The 4 and 1, 3 and 1 and 1. One. Again, we can solve the problem recursively. So I want to see this question again. Coin change. Hello, Passanjit. It's been a while. No. Right, so this is no combinations. So technically there are a total of 3 different ways. Alright, again we can solve the problem recursively. Let's denote the number of ways we can form the sum. For example, if coins 1 through 4, then solve 5, 6 in the recursive formula. Is that's still the same thing, right? Slightly different. So 1 plus 1 plus 1, so there's 3 different ways. Maybe. Yeah, okay, well that makes sense. If x is less than 0, the value is 0, because there is no solutions. If x is 0, the value is 1, because there is only one way to form an empty sum. Otherwise, we can calculate the sum of all values of the form solve x minus c, where c is in coins. The following code constructs an array count, such that count equals the value of solve for 0 less than equal to x less than equal to n. So such that count equals the value of solve x. for all of these different values. So we're including n, right? Yes, we are. X minus c is greater than or equal to 0. Then we can make the count something else. It's a smaller count. Otherwise, the number of solutions is so large that it's not required to calculate the exact number, but it is enough to give the answer modulo m, where, for example, in the above code, it suffices to add the line after the line. Ooh, what? Often the number of solutions is so large that it is not required to calculate the exact number, but is enough to give the answer mod m. Where, for example, m is equal to this. After this line. Yeah, okay. So, yeah, sure. Now we have discussed all basic ideas of dynamic programming. Since dynamic programming can be in different situations, we'll now go through a set of problems that show further examples about the possibilities of dynamic programming. Cool. Very cool. I want to try and do this problem. Now, coin change 2. Do I want to do coin change 1 again? Just for fun? Do I want to use C++ or Python? Man. I'll use Python for now. We'll use Python for now. And then see if I can do a C++ version. So just to make myself aware, I'm gonna up solve this problem by trying to write a little bit of a piece of paper. So we're looking at some function. Let's just call this solve, fuck it. Solve given x is equal to, now if x is, so it's going to be 0 when x is 0. It's going to be infinity when x is less than 0. And when x is greater than 0, we're going to take the min of coins in coins Min coins and coins of solve x minus c. X minus c. This is very messy. I'm gonna get rid of that. X minus c. Plus 1. X is greater than 0. X is greater than 0. Hello, Kizetsu. I am doing well. How was the internship? It was good. That's what I'll say. You just received a sweet automation position, which I'm super excited for. Do you see a LinkedIn update from? You'll see an update. You'll see a LinkedIn update from me soon. All right, bet. Let's go. Can't wait to see it. Well done, man. All right. Now that I have that, let me try this. Solve recurrence relation. Given x, where x is an int, we return a int. The solve function, if x is less than 0, then I don't think, wait, I think this is fine. If x is less than 0, then return math.inf. Probably got to import math. If x is equal to 0, we return 0, and if x is greater than 0, you return the min of something and something, right? So something and solve of x minus c. Which means to me, for c in coins, plus 1, min of maybe it's just some results, math.inf, min no, there's something else here. Ah, fuck. I didn't get that. I didn't fully digest that, huh? Okay, you return best. Okay. Whoops. Okay, so you call it best. Maybe I will call it best. Not return straight away, but some... Right, obviously. Okay. Take it a step back. So, else. Right, so in the else situation, yeah. Ideally what I do is if x is greater than 0, return, then I would do this. So then we return solve amount. And then that would be it. Whoops. Okay, yes. Equals. Second test case fails. Your output was inf, but you return. Okay. Right, so if, so not math inf, but -1. Oh, actually, that won't work either. So let's say result. So return res if res else. If res does not equal to math.inf, else -1. So this is a recursive solution that shouldn't pass all the test cases. Cool. To implement the I want to say this, right? So this is a good solution to have as the recursive approach, but now we introduce a array, which is our DP. As DP originally needs what? 0, because we're going all the way up to a given amount. So if it's 0, then if it's -1, best is equal to dp of x is equal to test. So if dp of x is equal to -1, return does not equal to -1, dp of x. Oh, right. Wait. We don't need len. The amount is just the amount. Right? Am I right? Solve the largest amount being amount. Index out of range. So it's amount plus 1. Or it just has to be x minus 1. Nope. Nope. That was not right. I gotta think why, man. I gotta think why. Can't leave that hanging. Oh, because you can't. You start with 0. You could have 0. All the way up to the amount itself. God damn. Okay, and then we also have the actual bot-up approach. So the bot-up approach is some dp I'm just trying to think. dp of 0 is 0, is that right? because coin change, when there is a zero amount, you return 0. So for 0, that's fine. For 1, we know it's going to be 1 plus. Come on, just tick, 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 tick. Trying to think. So, what's x again? X is the amount for all of these different amounts. If, so we'll just call them x. If x is less than 0, return so dp of x is equal to what the heck? I need to think about this. Hello, Shah Jilani. Long time no see, man. Alright, fuck. My problem is that is there anything that I return at all here? If I'm storing everything in the DP. I feel like at the end of the day, you know, like what I want to return is that DP of the very last value. There's something I'm worried about. Bro, are you at DP? I'm struggling at anagram. Oh, bro, you are at DP. I am struggling on anagram. It's alright, man. I struggle at anagram as well. Don't worry. It's just gonna take some time. Yeah, look, now the thing is, if x is less than 0, then what is the scenario that we have here? We don't return anything, right? There is no returning at all. Can we basically like do nothing? Actually, fuck it, we'll just say dp of x is equal to math.inf. Not sure if that's the correct way. We will think about this. X is equal to 0. And dp of x, well, we basically handled this. dp of x is 0. We handled this here. This I'm not too sure about. Best math.inf if the best is equal to min of best, and so dp of the x minus the coin, because you can assert that they should be filled by now, plus 1. So dp of x minus c is equal to best, I think. Of x is equal to best. So this is the best for x. Right. This tells me nothing, I think. X is less than 0, then it's just going to be. Would that ever be a scenario? No. It just won't be a scenario in this case, in this programming, in this program, in this for loop. It just never is the case. So there is no need for it. So yeah, I don't need it. Okay. Whoops. Let's see. Output 2 when... Yeah, okay. What did I do? Amount plus 1. Amount itself. Okay, I need to look at what the DP looks like after every iteration. Zero, 1, 2. And you expected an output of 3. Okay. Yeah, something's not right here. What would it be? So for x in this range, for this amount, so what's this? Amount is 11, right? 1, 2, and 5. So for when it's 0, it's just going to be 0. For when it's 1, it should be 1. But it's 0. I'm doing x minus c. So I'm doing 1 minus 1, which is 0, plus 1. If you have x minus, so 1 minus 1 minus 2 is negative 1. dp of negative 1 does exist to be negative 1. Plus 1 is 0, of course. Okay. So you need some condition here. If dp x minus c, if x minus c if 0 is less than equal to x minus c and x minus c is less than equal to amount plus 1 less than equal to amount, then you can do this. Otherwise you just won't do it, right? You just won't do anything, I think. So I could write this better, I think, as well. Right. Expected output of negative 1. If dp amount I guess best could be negative 1. Nah, negative. Can't do that. If amount is equal to mathinf, does not equal to mathinf, else negative 1. Like, I'm using two ways to describe this. I think I need to remove these. Okay, I could do this better. If x minus c, so because it's going to be always a bigger number, if this is less than 0, then you would continue, just not do anything. Right? Yeah, that's right. Yeah. Okay, so I solved this DP and understood it better. Let me see this dynamic programming solution. Yeah. I mean, okay, so I don't need the best. You make all the amount the maximum amount possible. That's fair. Yeah, you just make it the maximum amount possible. Yeah, which is very fair. Very fair. Very fair. Pretty smart. It's pretty smart. It's pretty darn smart. Okay. But this is my solution. We use a mathinf and we replace that. Good enough for me. Yank. We're gonna actually like head off now. We just redid coin change. We just redid coin change. attempt to. So I'm gonna call this attempt to. Given newfound knowledge from DP handbook .pdf hash page 75. Okay, and okay. So recursive approach. Python. The recursive approach for this. Actually, I don't need this, I think. Paste. Nope. Okay. I do need Python for this. And then a DP. And then a bottom-up DP. Hash. Using a memo. So it builds directly on top, so I want to somehow like emphasize these lines in the code blocks. This one, basically 3 lines. Notice there is only a 3-line change. Very cool. Okay. And this page we can delete, yes. Doesn't really matter. Okay. That's it, guys. We're gonna call it a night for now. I know this is... We've only done coin change 1. Yeah. But I also need to do coin change 2. Fuck. Alright, you know what? Maybe I'll come back to this. I'll come back to this before we finish the night, I think. The guy who pioneered DP wrote books about it. Very useful. The guy who wrote this handbook is very goated, because this is also very useful. But I want to finish coin change 2. I'm indecisive. I might just sleep. Not sleep, I mean just call it a night. Yeah, I might call it a night. Do it tomorrow. I think that's better. But yeah, the CSCS book. Very cool. Very good. Goated. Now we can party. Now we can party. Okay. Bye bye. Thank you guys. Thank you guys for joining. See you guys probably tomorrow. All right. Peace.